Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 60, and it is entitled Simple Machines and Efficiency. I'd like to tell you a story. It's a true story that happened at GPS during its centennial anniversary. In April 2006, Suzanne Smart and Catherine Bolden led the school in producing its spring musical, Peter Pan. Some of you may remember seeing that magical performance. One of the things that made that event so special was that the main characters flew during parts of the action. The part of Peter Pan was played by Emily Killian, and the roles of the Darling children were filled by Haley Cloudis, Zach Ranick, and Andrew Zellner. What made this production special for me was that Todd Wells and I led the flying crew in hoisting these characters up using ropes and pulleys. Here's how it worked. Before rehearsals began, the firm out of Las Vegas, flying by Foy, the same firm who flew Mary Martin in her defining performances of Peter Pan, installed a system of tracks, cables, and pulleys to connect to harnesses worn by the actors. Each flyer wore a special harness to which was connected a cable that ran around a small diameter drum that served as a wheel and axle. A separate cable was wrapped around a larger diameter of the same drum and connected to a rope that a stagehand could pull downward. The ratio of the radii of the drums was 3:2, which gave us backstage some mechanical advantage to lift the actors. Under ideal conditions, if Emily weighed 120 pounds, then I only needed to pull downward on the rope with 80 pounds in order to hoist her upward. On the other hand, I had to pull 3 feet of rope in order to raise her by only 2 feet. And that's the subject of today's lesson. We're learning how to calculate various characteristics of simple machines. The central concept along the way is conservation of energy as applied to input work and output work. You could think of me pulling downward as the input work and Emily being lifted upward as the output work. Along the way, we're going to figure out how to handle real situations involving friction and heat using a quantity that we'll call efficiency of the system. Let's begin by examining the 6 different simple machines. These machines fall into 2 different categories: the lever type machines and the inclined plane type machines. The lever type machines include the lever. You can see a brake lever or a shovel here, a snow shovel, which both serve as levers, the wheel and axle, and the pulley. The inclined plane types of machines include an inclined plane, which is a fancy word for a ramp, a wedge, and a screw. Each of these different simple machines have inputs and outputs. In other words, we can apply forces and exert those forces through certain distances in order to accomplish certain tasks. A simple machine uses humans, or in older days animals, to accomplish certain things, and we were limited by the amount of strength that we had to do the work. The tasks required a certain amount of work in the technical sense, force times distance, in order to accomplish whatever it was you wanted to do. We're usually limited by the amount of strength or force that we possess. So we trade in the force on the input side for distance on the input side in order to multiply the force on the output side. But this comes at a price of having to exert that input force over a longer distance so that the output force is larger but exerted over a shorter distance. In complex machines, there are usually combinations of several simple machines, and these days we frequently connect these input forces to internal combustion engines or electric motors and hydraulics to increase what a single person is able to accomplish. But under ideal circumstances, if there's 100% efficiency, the amount of work that I put into the system and the amount of work that I get out of the system are numerically equal to each other. So what this means is that the input force times the input distance is equal to the output force times the output distance. Your authors have chosen to call the input variables the effort, and they use an E to represent that. Whereas the output things, they deal with using the variable R for resistance. Writing this equation in terms of your author's variables, this is what it would look like. Your authors abbreviate the effort force with the letter E and the effort distance with the variables ED, and then the resistance, the output, as R for the force and RD for the resistance distance. And under ideal conditions, these things are equal to each other. This equation is essentially a statement of the conservation of energy. The amount of work that goes in is equal to the amount of work that comes out. There's another variable or set of variables called mechanical advantage. The mechanical advantage is the ratio of the output force to the input force. In other words, how much can I multiply the force as a result of using this machine? Because all machines contain some sort of internal friction, we're going to talk about the difference between the ideal mechanical advantage, IMA, and the actual mechanical advantage, or AMA. And these are defined in terms of forces and distances. Now I'll make a comment here that we see that the effort and the resistance and the effort distance and the resistance distance appear in different places in these ratios, so just be aware of that. The idea is that in general we're interested in trying to multiply our force, and the way I remember it is to think that the output force generally is going to be larger than the input force is. I will see that the output force is what goes upstairs in the mechanical advantage equation, and the input force is what goes downstairs. Your text does a pretty good job of telling you how to figure out what the effort distances or the resistance distances are for the various machines and what the mechanical advantage is for a pulley system. You'll find these on page 577 of your textbook. I've written here the different numbers to figure out the input and output distances for each of the simple machines. Let me draw your attention to the pulley here. If you're trying to figure out the ideal mechanical advantage, you look at the number of strands that are supporting the weight that's being lifted. So let's go back up and actually identify these things in the diagrams that we saw earlier. In this brake lever, the fulcrum is this screw that's right here. When you pull on the brake lever, then this distance that you pull is the input distance. On the other hand, the distance that the cable moves here when you pull it is the output distance. For the shovel, it's a bit more complicated. It depends on what is serving as the pivot point on the shovel. Is it your front hand? Is it your back hand? Are you lifting using your front or your back hand? Usually you're doing some combination of the two. If the shovel is actually in the ground and the back of the shovel is being pulled up, then the fulcrum may be in the ground. For the wheel and axle, this radius of the axle right there is sometimes depending on where the energy is coming in, it might be the input or the output. But this is the small radius, and then the large radius is the other, and depending on where the energy is coming in and where the energy is going out will determine what's the input and the output. In the case of Peter Pan, when I was lifting, I was pulling along the large radius, whereas Emily was being lifted along the small radius. For the pulley, it depends on these strands. So there's something that's connected over here to some object that's there that's being pulled, and I have 2 strands of that pulley that are actually lifting that object. So the mechanical advantage, the ideal mechanical advantage of this particular system might be seen as 2. For the inclined plane, the distance along this ramp is going to be the input distance, whereas the height of the ramp there is the output distance. For the wedge, the length of this wedge here is going to be the input distance, whereas the width of the wedge is going to be the output. And for the screw, if we look at the radius of the screw, the radius being from the center to the outside edge of the screw, that is our input distance, whereas the distance between each of these screws there is what we call the output distance, the pitch of the screw. So that's the way that you might measure things in looking at these simple machines. There's one more concept we need to talk about, and that's the concept of efficiency. In all real situations, I'm going to have to pay a tax to heat and friction in order to accomplish what I want to do. The efficiency, which we're going to use the letter E to represent, is going to be the work output divided by the work input. What we're going to see is that this will reduce to the ratio of the actual mechanical advantage divided by the ideal mechanical advantage. So these are important equations that you'll need to use when you come to the problems. Example 60.1. Using the pulley system diagrammed, a 300 kilogram mass is raised to a height of 2 meters by an effort force of 1650 newtons. The mass moves with constant velocity. A. What is the ideal mechanical advantage of the machine? B. What is the actual mechanical advantage of the machine? C. How far did the effort distance move? D. What was the input work? E. What was the output work? F. What was the efficiency of the pulley system? Now this technically is a block and tackle, which is a combination of pulleys that are used to lift this force right here. This force is the resistance. The effort comes at the other end of the string. What I see is that this weight is being lifted by two different strings here. That's going to be my ideal mechanical advantage. I have two lifting strings where I'm only pulling on one string there. So what's happening is I'm ideally multiplying this by a factor of 2. The amount of effort that I'm pulling, the amount of force that I'm using, ideally would be multiplied by a factor of 2 because I've got two strands lifting whereas I'm just pulling one strand. How much force am I lifting? Well, it's equal to the weight of this object. So the resistance force is going to be equal to the weight of this object, which is 3,000 newtons, M times G. So we've answered part A of this question. The ideal mechanical advantage of this system is equal to 2. Now the actual mechanical advantage is going to be the ratio of the resistance weight divided by the effort that I'm putting it in. So my actual mechanical advantage is about 1.8. Where did the rest of that force go? Well, it's going into friction in the pulley or in the form of heat as the different wheels turn. Now to figure out how far the force moved, the effort force, in other words, how much rope do I have to pull in order to raise this thing by 2 meters, what I have to recognize is whatever distance that this thing is raised is my output distance, and they told me that was 2 meters. They tell me that the ideal mechanical advantage is equal to 2, and so I can figure out the input distance using the ideal mechanical advantage. So now I'm going to solve this ideal mechanical advantage equation for the effort distance. In other words, I have to pull this rope 4 meters in order to get the weight to rise by 2 meters. Well, what about the input work? The input work is going to be the input force times the input distance. I get that I've did 6,600 joules of work in order to lift this force. What was the output work? Well, the output work is going to be the output force times the output distance. There were 6,000 joules worth of work done in order to get this weight, this 300 kilogram weight, lifted by 2 meters. So what's the efficiency? Well, the efficiency can be written in several different ways. It's either the ideal mechanical advantage divided into the actual mechanical advantage, or it could be the work out divided by the work in. Doesn't matter which one you do, you're going to get the same number. I'm going to do the work out divided by the work in. I get that my system is 91% efficient. If you want to do it the other way, you could say the efficiency is the actual mechanical advantage divided by the ideal mechanical advantage. And you see that you get the same number.